Okay, let's go to microelectronics joining, unless someone has a question on any of that. In order to make all the complex, fancy electronic devices and semiconductor chips and things like that that we have today, there's lots of bonding technology, because basically an electronic packaging is nothing more than composites technology. You have plastics, metals, ceramics, and semiconductors, all different types of materials, all put into one structure. As a result, it's a horrible thing to have to recycle. When we used to use gold on some of the contacts, then you could go into a refinery, and there's one down here in Attleboro, and you'd see all these old computers and printed circuit boards and stuff, and they just throw that into the furnace and stuff and burn off the plastic and end up with this low-grade brass gold alloy, and then they refine that, and you'd end up with gold bars and whatnot. However, nowadays that they've gotten more and more of the gold out of these things, there is no real value, and so now we just end up with landfills full of electronic equipment, which is getting to be a bigger and bigger problem. Nonetheless, the big thing nowadays is, in the electronics business, is what they call real estate. I have some printed circuit board, and I want to put as many chips as possible. And if you look at if you took apart a modern device, you can almost track within about a 3-year period over the last decade by looking at how small the capacitors are and the resistors and the chips and what type of technology they've used over the last 10 years to bond things to get as many things on a board as possible. Now, what I brought here are some multi-layer boards that are made up here in New Hampshire. This is one of the smaller boards that are made. It's a multi-layer board. It starts out, and this is not the same one, this starts out as a sheet like this, which is a plastic sheet that's got copper plating on both sides. And they then tin the copper. So it's plastic, copper, and tin. Actually, it's several layers of plastic too. And then they do photolithography and etch away, so they only get what they want. It has a bunch of holes in it. Actually, it doesn't have holes in it all the way through yet, but it has places for holes. And then they adhesively bond this stuff in a laminating press. So this is a single sheet. Don't cut yourself on it, but you can pass that around. You'll see that one says Cisco on it for Cisco systems. So a lot of your internet switching uses big boards like this. In fact, most of the boards, this is about a half-size board. Most of the boards they make, this printed circuit board might be a $500 or $1,000 board, depending on how thick it is. This one, you can look on the edge and you'll see kind of copper colored, and that's because it's got lots of different layers of metal in between. This one's a little bit heavy. If you want to see it, you can, but I'll pass this one around, which is one of the thicker ones, and you can actually see the copper layers, this composite structure to this whole thing. Some of them are a little darker. That's probably the power, where you put the high power through the center, and then you make all these connections in between. They plate down through the holes on these things. You don't see a lot of wires on here because the wires are all going through the thickness. So you just got solder pads here. And we're going to get to soldering a little bit later, but one of the ways people describe things in the electronics packaging business is the level of interconnect. And level 0 is the connection on the chip. So if I got a piece of silicon or a piece of gallium arsenide, and a modern Pentium 4 has 42 million transistors, there's interconnects between each one of those transistors. And that's all done by the photolithography and things that are done in the semiconductor manufacturing. And you've all seen articles on that. So that type of bonding is not too interesting to me because I'm not a semiconductor fabrication person. The next level, they actually call level 1. And level 1, actually I think they started out calling it level 1, and then someone realized, well, we do actually bond on the chip too. Level 1 is what I'm going to talk about today, and I handed out yesterday these tab bonded tapes. Level 1 is going from the chip in the center, making a connection to a pad a little metal pad that's been vapor deposited on the surface of the semiconductor, and that's got to now go to the package. And you've seen the packages. I passed some of those around before, but it can be a little semiconductor package like this. So I'll pass this one around. This actually happens to be a fairly unsophisticated, well, today anyway, pin grid array. So I basically put a semiconductor chip right in the center here. I got a gold surface, gold-plated surface. I would bond the semiconductor chip to the surface, typically with adhesive bonding. And then I have all kinds of wires that you can't see in this. If I slice this ceramic open, you would find all kinds of gold wires in between. Typically, that ceramic might be fired at 1,000 degrees in a furnace. So, you know, the gold has to not melt. You know, that's why they use gold. You can't use aluminum or something. But anyway, you then plug that into a package on a circuit board. That's 10-year-old technology. The reason Intel sells these things in these little packages is because in the early 90s, people said, I want more real estate. I don't want to waste all the space of those pin grid connections. I want to do direct chip attached to the printed circuit board. I want to mount the semiconductor right on the printed circuit board and just cover it with some epoxy or something to encapsulate it, to protect it. And that's called chip-on-board technology, because the level 0 is on the semiconductor. Level 1 is the semiconductor to its package. Level 2 is the package to the board, the printed circuit board, called a PCB, which is not a polychlorinated biphenyl, okay, but it is a printed circuit board in the electronics industry. There is a difference. Level 3 is a subsystem, and a subsystem package is basically, if I looked inside a VCR, I might find 2 or 3 circuit boards. And so a subsystem is how do you make connection from circuit board 1 to circuit board 2. And level 4 is system. A VCR is not very useful without a TV, right? So connecting from the TV to the VCR is the interconnect, the electrical interconnect at the system level. If you're talking about a great big system like an Aegis missile system, you got semiconductors, you got semiconductors to the package, you got packages to the boards, you have some subsystems, which is an electronics module that fits in a rack. And then as each one of those modules connects to each other module in the rack, that's the system interconnect. So there's 5 levels of interconnect in order to create some modern electronic system, whether it's an Aegis missile system or whether it's a internet router or whatever. So there's lots of different levels of interconnect. We're not going to talk too much. We're not going to talk any about this because this is basically photolithography and vapor deposition, putting metals down to make semiconductors. This is what I want to talk about today, level 1 interconnect. We'll later talk about package to board, and I won't talk about levels 3 and 4 because A, I don't know anything about it, but also you've hooked up your VCR to your TV and you know basically what those types of things look like, although they get more complex in bigger systems. But let's go to, there's something called Rent's rule. And Rent's rule is a relationship between the input-output, the I/O, to number of circuits on a chip, on a semiconductor chip. It turns out that if you want to read about Rent's rule, this is in your bibliography, but this is actually an old book. It's 1989 now. which makes it ancient technology, although I've heard that Tamala has come out with another edition of this. But Tamala at the time worked for IBM. This is Microelectronics Packaging Handbook. It's a fairly thick book, and it goes through primarily levels 1 through 4. It doesn't talk about level 0 in terms of interconnect. But if you go in here and you look up Rent's rule, there's a formula for it. You find that over a couple of orders of magnitude, if the number of circuits raised to some power, like about a third times some constant, equals the number of input outputs. How many wiring connections do I have to make to that chip? So if I go back to a very, very old, this is probably an old memory chip module, because this has, I don't know, if I look at count the leads along here, I don't know, this may have 48 leads. Okay, this was probably some sort of kilobyte memory chip back 15 years ago. Package, you know, now we got, you know, 64 gigabytes and 250, you know, 56, not gigabytes, megabytes. You can get a lot more. In fact, I look back and I notice you can now get a Pentium 4 that has a 2 gigahertz clock speed. And I remember the first Mac 2 I ever bought back when my son was in high school. My oldest son was in high school, so we're talking 10 or 12 years ago. Actually, not even that long ago, 10 years ago. It was a 2 megahertz computer, okay? But if you go back to the original IBM PC, everybody, I remember not being able to afford the 20 megabyte hard drive. Okay? I also remember when I had a VAX and the 1 megabyte disk, replaceable disk, were this big around. I mean, they were 2 feet in diameter. Okay, so things have obviously gotten smaller and smaller, and it's pretty impressive to see the ever-marching onslaught. However, there are limits to that. One of the limits people thought was a pretty serious limit for Rent's rule about 7 or 8 years ago was, how do I make more than about 400 connections, I/O connections, on a little chip that's only 1 centimeter on the side? Well, people can say, why don't you just make a bigger chip? Now, it's been a couple of years since I've been to Intel, but I remember 4 or 5 years ago, whenever it was, I was at Intel right before the Pentium 3 came out. The Pentium 3, if I remember, was actually 2 chips on 1 package. They couldn't make a 3/4 inch chip to put everything on 1 package. They made 2 1 centimeter, actually one chip that was about 1 centimeter on a side, and another one was about a 1/2 square centimeter. And the reason you can't do that is because you've got dissimilar materials here, and they heat up at different rates. And these semiconductors are not very ductile; they're very brittle. They also have solder connections, so if they get very hot, you're going to destroy things. Now it turns out that, so let's look at it sideways here. I've got, let's just say it's silicon rather than gallium arsenide, which is worse. And I've got to bond it to this essentially aluminum oxide ceramic substrate. It's actually about 94% aluminum oxide and has some manganese oxide in it. And this has got all the wiring connections. And I'm going to have to make a connection between about 400 connections for a Pentium 2 or a Pentium 3. I don't know how many are on the Pentium 4. But there are about 400 connections that have to go from the chip to that package. And the problem is, in the early 90s, these chips were getting to the point, they're about 1 square centimeter, and when they're screaming along, they develop about 10 watts, which is 10 watts per square centimeter. Now, how much heat is 10 watts per square centimeter? We're going to go through this when we get to fusion welding and flames. But to give you an idea, a Bunsen burner is about 10 watts per square centimeter. So if you want to hold your finger in the flame from a Bunsen burner, okay, you would probably burn it fairly quickly. A semiconductor chip, when it's running, you know, as hard as it can, is going to generate about 10 watts per square centimeter. You've got to carry that heat out. And so there's lots of bonding technology in here. One is you got to bond the chip to the substrate. Forget the connection. You just got to get good thermal contact between that chip. Back in the old IBM 360 computers, they actually used to have copper rods that came down and sat on top of the chip and had helium gas going through the copper to carry the heat out. Now this was a much simpler chip, but nonetheless, you had heating problems. What people still tend to use is an adhesive, a polymer adhesive that's got silver powder in it. So you end up with a lot of silver powder, and silver has good thermal conductivity, and hopefully you have now some metal-metal contact. And so you've made a little composite adhesive, and the silver powder is sucking the heat away into this substrate. And you do all kinds of things. And you look inside a circuit board, and you'll see these big heat sinks sitting right on top of the main processor, right? And so you're trying to do that, and you got little fans and things like that. May not be a lot of power, but it's a fair amount. Think about it. A light bulb, a 60-watt light bulb, gets pretty warm, right, to the touch. Now, warm to the touch is about 140 degrees, that you don't want to hold something at 140 degrees. That's because if you touch something for 10 seconds at 140 degrees, you'll burn your hand. If you only touch it for a second or two, it's not so bad. Typically, you run the water in your house, in the hot water, at about 140 degrees. If you were to turn the water on full hot and get in the shower for 10 seconds, you'd come out red with a slight burn. Okay? So you mix it with cold water, right? And you don't run, you know, you can put your hand under 140 degree hot water, but you don't keep it there for 10 seconds or so. At 180 degrees, you will burn yourself in a fraction of a second if you have good contact with the skin. At 160, it might be 1 second or something like that. And that's why the woman got $3 million or whatever it was from McDonald's. Remember the story about the woman who put the coffee, you know, she was at the drive-up window, she held the coffee between her legs and it spilled and she got very serious burns. And why did McDonald's have to pay? First thing you heard in the media was everybody thought, this is ridiculous. Why should McDonald's pay because she spilled the coffee? Well, if you know the whole story, McDonald's had a policy of brewing the coffee at 180 degrees. Because if you've ever been to a McDonald's nowadays, you notice in the morning, it's mostly retired people who go there and meet each other and have a cup of coffee and read the paper and talk to each other. And, you know, that's, if you go to McDonald's in the morning, they come and as they're reading the paper, they let the coffee sit, and then they come up to the counter and say, my coffee's cold, I want a new cup of coffee. So McDonald's had a policy of brewing at 180 degrees. 180 degree water will burn the skin within less than a second. They had 300 complaints from people about burns, less serious than this woman's, because the coffee was too hot. But they kept their policy of giving you a drink that was hot enough that if you spilled it on yourself, you would essentially instantly burn yourself. Okay? So, did McDonald's deserve a punitive judgment? You can decide, you can be the jury, but don't just believe what you heard in the media where they said, well, this woman spilled the coffee on herself and she got $3 million from McDonald's. If you actually hear what the jury heard, I wasn't involved in this, but it's a little bit different story if you hear the other side of it. Okay? Now you can still say she shouldn't have been driving away with the coffee between her legs and things like that, and that's true. Okay, but the jury has to decide that. But McDonald's, you know, the jury decided McDonald's shouldn't be serving coffee at 180 degrees, and they don't anymore. Okay, so whether that's good or not, but I don't drink coffee, so it doesn't matter to me. Drink orange juice; it won't burn you at all. In any case, so we have to make a good bond here. We can talk when we get to transit liquid phase diffusion bonding, how you can actually make a true metal-metal bond at low temperatures by diffusing things away. We'll get to that when we get to soldering. But I want to talk a little bit about these input-outputs. One way to do this, if this is 1 centimeter on a side, which is about 400 thousandths of an inch, right? So I have 1.6 inch perimeter. Basically, on each chip, I'll have little square pads that I'm going to do my wire bonding to. So I take my little 1 mil gold wire, 25 micron or 20 micron gold wire, and I'll come in and I'll do my thermal compression weld. Now, in order to take the little sewing machine type of apparatus that feeds the wire in there and presses it down to a thermal compression weld, I need to have about 7 thousandths of an inch spacing center to center on those pads. The pads are about 4 thousandths of an inch wide, square, which is a 1/10 of a millimeter. That's not very big. But in order to not smash the wire that I just made the bond on right next to it, that little sewing machine head type of head that comes in to feed the wire in has to have a clearance of about 3.5 thousandths on either side, which is 7 thousandths center to center. Okay. You just can't make it any smaller. If you do, it just crumples when you try to apply the pressure for the thermal compression weld. So that means that if it's 7 thousandths on center, that's about 50, or if you want 57 or whatever the number is, bonds per side. So I might get 350, not 350, that's not 350, 240 IOs with wire bonding. Well, that's not good enough. So what people can do is they can do not what we call, this is called perimeter bonding, because I'm just going to make these little squares all the way around. I can put a second row in, but now I'm losing real estate on my semiconductor chip. I could have another 1,000,000 transistors on there, right? So I'm losing real estate on the chip. But I might be able to get wire bonds, and now I have another wire down here that leapfrogs over that, and it's a little taller. But I'm losing area on my semiconductor chip. I'd like to have an even smaller pad. And so wire bonding is one thing, and it'll get you up to maybe a little above 200. You can then go to tab bonding, which is tape automated bonding. And that's the toy I gave you. That tab tape is a piece of polyimide plastic, a relatively high temperature plastic, because you're going to solder to it. It's going to have to take soldering temperatures. And if I look at this, here's my chip in the center. I actually have already made lines. Each one of these little wires is about, on the tab tape, here's my chip. Each one of these little wires, which is made by photolithography, same way as that great big circuit board laminate that I sent around, basically same type of photolithography but on a smaller scale. It's about 2 thousandths of an inch wide, and they're on 4 thousandths centers. Okay? Center to center is 0.004 on these. So going around my chip, if my chip is 400 thousandths on a side, 1 centimeter, the perimeter is 4 times that, it's 1.6 inches, and that's 400 IOs for a tab tape. That's better than the wire bonding. And in fact, I think once upon a time, I didn't count them, but I estimated them, there's about 360 on this. This is a Pentium chip. Now, what happens is, you can't see it on the screen here, but if you take your own, you'll actually see how the wires come up across here in the plastic, and then they take different angles, and then you have this row right in here that you can see. See these rows on the 4 sides? The ones inside in here are called the inner lead bonds, and these are called the outer lead bonds. Very clever technology, naming technology here. And basically, this is on a piece of 35 millimeter film, or something like a piece of 35 millimeter film. So it comes on a big roll. You put the chip on. Intel will sell you this, and they've already made the interlead bonds. and you basically put this right on a circuit board with a little adhesive underneath it for good thermal contact. You come in with a very expensive machine. Everything's expensive in the semiconductor industry. And you basically come in and you squeeze these outer lead bonds into the surface of the contacts on the printed circuit board, and you do it with a little bit of heat. You actually solder the things together with this head of hot metal, and it's a proprietary material called tungsten. Okay, if you ask them what it is, I can't tell you what it is, but it's tungsten. Okay, so you have this heated tungsten thing, and you can go in and do one side at a time. You got 4 sides here, and you can come in with just a single tungsten piece and make 1 row of bonds at a time. And now you only have to worry about whether your hot tungsten piece comes in square and it's not cocked sideways, right? So you get equal pressure across all 90 bonds across that side. Or you can do, and that's called gang bonding of the whole thing. Wire bonding is 1 at a time, and it takes a while. They can only do about 10 a second. That sewing machine only moves so fast. But the gang bonding, you could do 100 on a side all at once. Or more commonly, they actually come down with a square piece of tungsten, and they try to do the whole thing at once. And then you come down after you've done the bond. Well, now, if you're doing the whole thing, now you have all kinds of alignment problems, because these things may be 2 thousandths wide, but they're only about 1/1000th of an inch thick. So you've got to have this whole thing heated up, relatively uniform in temperature, and not have any distortion within a few microns. Okay, so it's pretty precise, because you get 1 bad bond and you got a piece of junk, and that piece of junk would have been worth a couple $100, right? So it's not easy to repair these. Some of them can be repaired, but it's not easy to repair them. And then you come through and you shear off the thing, and the rest of the tape is junk. Okay, it's just the rest of the tape is just a holder to allow you to do this. Okay, I guess that's enough for today. Thanks.